Picture a mathematical mystery that defied the sharpest minds of the 18th century. For hundreds of years, scholars had unlocked formulas to solve equations up to the fourth degree. But the quintic, a stubborn fifth-degree polynomial, stood unconquered, its secrets taunting the greatest mathematicians. Was a universal solution possible, or was it a fool's errand? Then a daring 18-year-old genius stepped forward, delivering a proof that shattered the quest for a general quintic formula. His radical ideas didn't just solve a problem, they sparked a new branch of mathematics, illuminating ancient geometric riddles and laying the foundation for the cryptography that secures our digital world today. This is the story of Évariste Galois and the birth of Galois Theory. The story begins in 1799, when the legendary Carl Friedrich Gauss unveiled the fundamental theorem of algebra. This monumental theorem declares that every non-zero, single-variable polynomial of degree n with complex coefficients has exactly n complex roots. It's a bold promise. A quintic has 5 roots, a quartic has 4, and so on. But knowing these roots exist is one thing. Finding them is a far greater challenge. How do you uncover the roots of a quintic? At the time, mathematicians like Joseph Louis Lagrange were racing to crack the quintic. They had mastered quadratics, cubics, and quartics, using operations like addition, subtraction, multiplication, division, and radicals. But quintics were rebels. The methods that tamed lower-degree polynomials faltered. Gauss himself issued a challenge. After years of failed attempts by the world's finest minds, he wrote,
"It appears more and more likely that this resolution is impossible and contradictory."
But everything was about to change with the arrival of a bold young genius, Évariste Galois. Galois was born in 1811 in a France torn by revolution and Napoleon's shadow. By his teens, Galois was no ordinary student. While others played, he devoured mathematical texts that baffled seasoned scholars. At just 15, he pored over Lagrange's intricate works on equation theory, his mind alight with possibilities. By 18, he crafted a daring proof that no general formula using radicals could solve quintics. Heart-pounding, he sent his work to the French Academy of Sciences, only to face rejection from the mathematician Augustin Cauchy. Why? A Norwegian mathematician, Niels Henrik Abel, had already published a similar proof. Galois' work seemed brilliant but redundant. Yet Galois was undeterred. Studying Abel's proof, he spotted a gap, a question no one had dared to ask. Why are some polynomial equations solvable by radicals at all? Galois' genius was to see equations not as mere numbers, but as patterns of symmetry. In mathematics, symmetry describes something unchanged under certain operations.
Picture a square. Rotate it 90 degrees or reflect it across its diagonal, and it still looks the same. Galois applied this idea to the roots of polynomials, asking, what permutations can we perform on the roots without breaking their algebraic relationships? Consider a quartic polynomial with 4 roots, expressible using radicals. These roots are bound by algebraic relationships. These are basically equations, like sums or products. Galois began thinking, are there permutations that preserve all these relationships? There's only one, the identity, the do-nothing permutation that leaves everything as is. But what if we focus only on relationships yielding rational values? Suddenly, 8 permutations qualify. These are not random 8. If you plot the roots on the complex plane, each of these elements represent a certain operation. These operations are the symmetries of a square. They form a group.
In the nutshell, if you randomly choose 2 elements within a group, the composite would also be in the group. Moreover, for each element within the group, There is always one element within the group that brings to the do-nothing permutation, which we call the identity.
Now consider a new radical, like a square root. The group shrinks to 4 permutations, forming a subgroup. Add another radical, and the group shrinks further, eventually collapsing to the identity.
These radicals that we added are closely related to the choice of radicals that we need to express the roots of the polynomial. In fact, each time we consider a radical, we are generating a larger field than previous. This process is called field extension. Galois noticed this trend, and his genius culminated in the fundamental theorem of Galois Theory, a profound insight that ties field extensions to symmetry groups. In particular, he stated that there is a one-to-one correspondence between the intermediate fields and the subgroups. This means that if we add the radicals in a different way, the tower of subgroups would be different.
With this theorem, he could concentrate on the behaviors of the symmetry group, which was subsequently known as the Galois Group, and all its subgroups. By doing so, he knew that each subgroup would correspond to a new radical to be built, and until he reached the identity group.
But how do you find the right chain of subgroups? Galois approached this in a different perspective. Besides the subgroup which preserves algebraic properties, how do the rest of the symmetries behave in these relations?
Well, in our example, they all flip the sign. To be precise, it sends the radical to its conjugate. Galois studied tons of more Galois groups and summarized that the Galois group sends the radical to one of its conjugates within each intermediate field. It follows naturally that in order for this tower of extension to make sense, each layer must include all the roots. Therefore, it should be natural that when we build the first radical, say alpha, we need to include all its conjugates, which are the roots of unity. If there is a radical that fits into the chain, then we should be able to find a subgroup of the Galois group that fixes every element in this field. Let's call this group N. But which elements are contained in N?
Now take 2 random elements from the Galois group and consider the composite G inverse, H inverse, G, H. This composite means we do the operations in the following order: H, then G, then H inverse, then G inverse. Order of operation is particularly important because not all groups are abelian, which means that reversing the order might result in a different solution. So H sends the radical to one of its conjugates. This would be alpha times zeta to some power. The similar goes the same for G. Then H and G are reversed, giving us alpha again. This means that this composite actually belongs to the subgroup N. This is actually a strategy to find the subgroups. N is just the collection of all the possible composites of this form. These composites are called commutators. This kind of group has a special name: normal subgroup. By repeating the process on N and recurrently, we can easily find the chain of normal subgroups of the Galois group, and hence all the intermediate fields. Galois then developed this idea further, which would later become a set of criteria to determine the solvability of a random polynomial, not purely limited to quintics.
But first, let us remind ourselves of the problem. We are trying to prove that in general, a polynomial of degree 5 is not solvable by radicals. Luckily, proving something does not work is simple. We only need to provide one counterexample.
Take a general form of a quintic. Its roots would automatically satisfy some symmetric properties relating to the coefficients. This means that these properties are all preserved under the S5, the group of all permutations with 5 elements. It follows that the Galois group would always be a subgroup of S5. However, if the roots are more related, then there are more relations that need to be preserved. For example, in the previous example, we have further algebraic relations within the field of rationals that have to be preserved, so the Galois group has shrunk to D4 instead of S4. In the most extreme case, the fifth roots of unity, which is given by this polynomial, has a cyclic Galois group which has only 4 elements. In general, the Galois group of a n-degree polynomial would always be a subgroup of Sn. The less related are the roots, the bigger is its Galois group, and hence more likely to be Sn.
Galois began with a quintic having 2 complex roots, which are conjugates. Their sum is real, so at certain point the Galois group must contain a transposition that swaps these roots. To continue, we must rely on one of the most important observations within the Galois group. The Galois group of a quintic must include at least one 5-cycle. A n-cycle is a cyclic permutation involving n elements, where all n of them are permuted to another element with no fixed elements. Since the Galois group contains at least one 5-cycle and one transposition, it must also contain all the composites due to the property of a group, and also the composites of the composites. By accounting for all the combinations, you will find that this Galois group must contain at least 1, 2, 3, 4, and 5 cycle. The only possible subgroup that has this property is S5 itself.
This chaotic group suggested roots so loosely connected that radicals were out of reach. But just how chaotic is S5? Galois pressed deeper, testing S5 with his commutator method.
He took 2 3-cycles, say tau and sigma, and computed their commutator. Tracing the elements, this yields another 3-cycle. The pattern emerged. Every 3-cycle in S5 was a commutator of 2 other 3-cycles. To fully visualize this, you just need to replace the letters with the numbers you want. This was a roadblock. A normal subgroup of S5 containing any 3-cycle had to include all 3 cycles, since commutators define the group's structure. Building a chain of normal subgroups to reach the identity was impossible.
Galois paused, his candle burning low. The 3 cycles were the villains, locking S5 into a structure that couldn't shrink properly. For quadratics or cubics, the Galois group allowed a chain of normal subgroups to the identity, matching a tower of field extensions with radicals. But in S5, the 3 cycles formed an unbreakable barrier. This was his proof. A general quintic with Galois group S5 was unsolvable by radicals. Unlike Abel, who proved the impossibility, Galois theory provides a framework to distinguish whether a polynomial is solvable by radicals. Some quintics are solvable if their Galois group avoids 3 cycles, like the Frobenius group, dihedral group, and cyclic group, depending on the roots relationships.
For example, this polynomial, x to the 5th minus x minus r, has a Galois group F20 if r is equal to 2,759,640. In such cases, its roots can be expressed in radicals. This Galois group does not involve transpositions. Every element within the groups permutes at least 4 roots, avoiding 3 cycles. Other than this example, there are still infinitely many quintics that are solvable by radicals, but how can we spot them? Galois theory offered a universal test. Examine the Galois group and its normal subgroups to determine solvability.
Galois' brilliance didn't just crack the quintic puzzle. In a single feverish paper, he laid the foundation for Galois theory, solving ancient problems like constructing a regular heptagon, doubling a cube, and trisecting an angle all at once. Sadly, he himself could not see this success. In 1832, at just 20 years old, Galois' story took a heartbreaking turn. He was caught in a duel. The night before, knowing death loomed, Galois poured his soul onto paper. In a frantic scribble, he wrote his mathematical visions, scrawling, "I have no time," in the margins. Those pages held the seeds of modern algebra. The next morning, a shot rang out. Galois fell, wounded, abandoned, and died. Buried in an unmarked grave, his genius seemed lost forever. But his ideas, they were just beginning to ignite. In the final diary, he wrote, "Go to the roots of these calculations, group the operations, classify them according to their complexities rather than their appearances. This, I believe, is the mission of future mathematicians. Galois' notes, rediscovered years later by Joseph Liouville, set mathematics ablaze. Published in 1846, they unveiled a revolution. The world was stunned. Galois theory unveiled the hidden symmetries of equations, birthing group theory, and reshaping mathematics. His vision lives on. Today, Galois theory powers cryptography, securing your digital world with unbreakable codes. It reveals symmetries in physics, from quarks to galaxies. The fundamental theorem of Galois theory, linking groups and fields, is a cornerstone of abstract algebra, taught worldwide. Évariste Galois, the rebel who saw beyond numbers to their symmetries, left a legacy that burns bright.